Cool. Okay. Right. Thank you for your patience. I'm Alastair Smith. I run a group in Cambridge called the Cambridge Software Craftsmanship Community. I started at Redgate about 3 weeks ago, and I've declared war on legacy code. So, why refactor? There's a couple of good reasons for refactoring. We can remove duplication to ensure that there's only sort of one concept or one implementation of each concept in the application. We can improve maintainability so that the application is easier to work on, add new features to, fix bugs in, etc. And we can improve the design of the existing code without changing the behavior. That's sort of the dictionary definition of refactoring, really. And refactoring is a bit of a journey, really, so it needs a destination. And the destination that I like to consider when I'm refactoring is to refactor to the solid principles. So for the rest of this talk, I'm going to assume existing knowledge of the solid principles. There are some references at the end if you're not familiar with them or they're a bit hazy or whatever. But I'll go through a very brief sort of definition of them as I go through. So first up is the single responsibility principle. And for me, this is really the sort of prime directive of programming. It's sort of cause number one, the thing that we must really focus on. If something does more than one thing, then it's going to get very confusing very quickly about what that thing is actually supposed to be doing. And there are a number of refactorings that you can do to refactor towards the single responsibility principle, most of them around the concept of revealing intent. And they're things like renaming variables. So if you've got a variable that is just called x, but actually you realise that it's a loop variable, for example, or it's the total sum for the current calculation, then just go ahead and rename it and tell everyone what this variable actually is. You can introduce constants, so if you've got magic strings in your code base, or if you've got slightly odd sort of expressions or regular expression definitions or anything like that, you can introduce constants of those to give them an actual name rather than just saying this is the thing and let everyone figure out what it is from there. You can introduce variables as well. If you've got a complex Boolean expression, for example, then it can be useful to break that up into chunks and say, well, this bit is the equality check for these two things, are they equal? This bit is the equality check for these two things, are they equal? And then compose the two variables into an AND statement. It just makes the code a bit more readable. You can also extract method as well. So you can pull out an entire block of code from an if statement, for example, into a separate method and give that a really nice, clear name to say exactly what that method is doing. You can extract classes as well to achieve the same sort of thing. You can, if you find that you have more than one responsibility within a class, you can pull out one of those responsibilities into a second class and give that a more descriptive name. All of this is really about naming things, giving things sensible names that make it clear what the code is supposed to be doing. And a technique that I learned in a workshop that I helped run over the summer was to use fully descriptive names. So if you're pulling out a method, for example, from an existing block of code, and that method is completely new, then you can give it as descriptive a name as you like. And it's very useful to say, this method does this, and it does that, and it does the other, and it throws an exception in that case. And yes, you end up with a massive method name, but it's very clear what it's actually doing. And then you can start using that as a further jumping off point for more refactoring, because you've got more responsibilities in there. You should also factor out regions and partial classes, something that I've seen in previous code bases, and particularly in sort of some demonstration applications that you get for things like WinForms and web forms, very keen on partial classes and sometimes regions. If you find a need to put regions into your code, it's probably because the code's doing too much. So steer clear of those, factor them out into different things. Partial classes are quite often used for similar things. This class is defined across two files, but it does one thing in this file and it has another set of behavior added in this file. Really, they're probably two separate classes and should be kept separate. There's also an interesting blog post that I read earlier from Uncle Bob called Extract Till You Drop, which talks about taking this to the absolute logical conclusion of extracting out methods over and over again until you can't extract anything else. And there's a bit of an interesting discussion over whether that's actually useful or not. Sometimes some people feel that it gets a bit too wordy, other people feel that it actually increases clarity because each method has this sort of one focused purpose, really. So, the open-close principle. The open-close principle basically allows code to be extended without modifying the code itself. That's the sort of ultimate aim of it. A good refactoring that you can use to get towards the open-close principle is to replace branching with delegation. So if you've got a method that has if this, then do that, else do the other thing, then you can pull out those two methods into a separate thing and then inject that behavior through the method or through the class constructor. Injecting behavior and wrapping behavior are very useful techniques for getting towards the open-close principle. And some good examples of these are common design patterns like the strategy pattern and the decorator pattern and the composite pattern as well. They will all be very useful in this kind of situation. I will most likely come back to design patterns in a later talk because I really feel that they are the kind of bricks and mortar that developers work with, and that a good understanding of how they work and where they're applicable is really important. The Liskov substitution principle. This sort of allows us to reason about our code. Type safety varies across languages, so dynamic languages don't really have any type safety at all. Static languages have quite a lot of type safety, and then functional languages like Haskell have all the type safeties that you could possibly want. When we program to the Liskov substitution principle, we can start to get towards functional-like levels of type safety in languages that don't natively support it. It allows us to say, if I treat this thing like this thing that it's supposed to be, even though it's a subtype of it, it will still behave like the thing it's supposed to be and it won't blow up. A good way to refactor towards the Liskov substitution principle is to replace inheritance with delegation. So if you've got a complex inheritance hierarchy, which in itself is fairly evil because the mental load is so great in trying to process it that it's just cheaper to remove it altogether, really. If you've got a complex inheritance hierarchy, you can start to peel that apart and inject the behavior, delegate the behavior to new classes that implement that particular bit. And you can either inject it directly at the beginning, or you can just create an instance of the new class that you've created. The main thing to do is to break the inheritance and move towards a more sort of composition type approach. Interface segregation principle. This brings specificity to our code bases. It allows us to say this bit of code acts in this way and this bit of code acts in this way, and I'm only going to treat it in this way and interact with it through that interface. So there are a few things that you can do to refactor towards this. You can remove any interface inheritance that you have already in the code base using similar techniques to the Liskov substitution principle refactorings. You can factor out regions from both your classes and your interfaces. If you've got regions in your interfaces, I don't know what's going on there. Remove any not supported exceptions that you've got in your code base, by which I mean if you've got a class that's implementing an interface and only part of the methods are implemented and the rest are throwing not supported exceptions, there's probably two interfaces going on there, and this class only cares about one of them. Finally, you can extract an interface. So if you've got a class that has a few different ways of looking at it, then you can extract interfaces from that class for those different views, essentially. Finally, the dependency inversion principle. This is really useful because it allows us to state our expectations of our code up front. it can be realised through dependency injection and the associated concept of a composition root, which essentially says at the beginning of the application we take all the blocks that make up the application, stick them together like a Lego model, and then hit run. It's a really nice pattern, it's a really nice way of looking at, of building code. A good way of refactoring towards the dependency inversion principle is to extract pure functions. Can anyone give me a definition of what pure function is? Toby? Yeah, that's part of it. Sean?
Repeatable. That's how actually like the same sort.
Yes, it also takes everything that it needs. Yes, exactly. So by pulling out pure functions, because they're completely independent of the world around them, they take all the dependencies that they need, they have no side effects. You can then move them around as you need and inject them into other things. When you've got collections of related pure functions, you start to end up with classes that represent those concepts. So where does all of this lead? A lot of this involves replace foo with delegation or extract foo. What does this really result in? Well, it moves rigid code towards flexible code, it moves fragile code towards robust code, and it moves scary code that you're a bit afraid to touch and change towards cuddly code that you're quite happy to work with. All the promises that we software engineers make about robustness and flexibility and reuse are really realised through the solid principles and through solid code. So I really think that when refactoring, this is the best destination for our refactoring efforts. Thank you very much for listening. Are there any questions? Graham?
I was surprised that you're on your interface segregation. You say no interface inheritance. Is that realistic? I mean, you need everywhere? There should never be any interface inheritance?
Yes, what you can do instead is to implement both those interfaces separately. The thing about interface inheritance is that it's a bit of a leaky abstraction, because you're saying that if this class implements this interface, I also expect it to implement this interface as well. So if you've got an interface that's an iResource, for example, and you define that to implement iDisposable, what you're saying is that anything that implements iResource is going to be iDisposable, which may not be the case. You may want to implement some purely native bit of code with the iResource interface.
But wouldn't it be fair, for example, if you had a stream and a sequel stream?
And what stream, sorry?
A sequel stream that isn't also a stream.
Sorry, what's the other type of stream?
So a stream, so let's say you had a stream that you can read stuff from.
Yes.
And then another one which you can also seek in.
Oh, I see. Right.
It makes no sense to be able to seek without also being able to read.
Yes, indeed.
And yet at the same time, you don't, from your other thing, you don't want to have the iStream include seek, because that might throw in a not supported exception if it's coming in from.
Yes, indeed, and we see that in the stream classes in .NET anyway, because there are some that you can read and some that you can't seek to because of the very nature of what they are. Yes. Sean?
Another counterexample would be if you wanted to have an equatable for an interface. So if you have 7 different things still looking at the same interface and speaking to each other, with regards to the definition from interface, if one's got equatable and interface not mean to each other?
Maybe, yes.
It might be intervals. You might have different ways of representing intervals in space, and you still have to check that they are the same distance, for example.
Yes. I don't think I fully understand the example.
So you can have a polar interval, a confusion interval, so to speak.
Right.
And you'll be able to compare them. So you want them to be equatable to the interface, not their representation.
Yes. Okay. Anyone else? No? Okay.
Thank you.
Cool. Thank you.